Welcome to Algebra 1, Chapter 4, Section 3, Patterns and Nonlinear Functions. Let's do a quick review of patterns. I don't think this is difficult for any of you, but take a look at this. So we have problem number 1, 1, 2, 4, 8. Do you know the next number in the pattern? Well, we're doubling each time. 1 doubled is 2, 2 doubled is 4, 4 doubled is 8, 8 doubled is 16. Problem number 2 over here on the right. We go -8 to 4 to -2. Well, it looks to me like we're taking the opposite and halving it. So we're multiplying by -1/2 each time. So my answer here is going to be the problem number 1. Next problem, 1, 3, 9, 27. Those look like multiples of 3. 1 times 3 is 3, 3 times 3 is 9, 9 times 3 is 27, 27 times 3 is 54. In problem 4, we have 1/2, 1/4, 1/8. What's the next in the pattern? Well, the denominators are being doubled each time. So if I double 8, I'm going to get 1/16. And for number 5, the next shape in the pattern below has how many blocks? Well, we have 1 block, 4 blocks. 3 by 3 is 9 blocks. But look what's happening. I started with 1, and then I added on blocks. I started with 4, and then I added on blocks again. So I start with 9, and I add on blocks. I'm going to have a 1 by 1, 2 by 2, 3 by 3, and my next one will be a 4 by 4, which has 16 blocks. So there's a couple things I really need you to understand. So I call this essential understanding. And what I need you to know is that we have functions, and up to this point we've only talked about linear functions. In this section we're going to talk a bit about nonlinear functions. And like linear functions, they can be expressed words, with tables, with equations, with ordered pairs, and with graphs. So a linear function is a function who has a line, but it's a non-vertical line. A nonlinear function is a function whose graph is not part of a line at all. There's no lines. So here's your definition. A nonlinear function is a function whose graph is not part of a line, nor is it a line. A linear function is a function whose graph is a line or part of a line. So which of these 4 graphs are nonlinear? Did you pick them out? This one is nonlinear, as well as this one. The other 2 are linear graphs. As you see in this example, I have a problem dealing with pizza. In this we have the area A in the square inches, not a square pizza, but square inches, is a function of R. The cost in dollars for the sauce of a pizza cost is a function of the weight in ounces. We're going to graph these functions and decide if the functions are linear or nonlinear. So we know that they are functions, but we don't know if they're linear or nonlinear. So we're going to go ahead and make graphs. As you can see, I made graphs. I used area as a function of radius and cost as a function of sauce. So in the second one, the sauce is my independent and the cost is my dependent. In the first one, the radius is my independent and my area is my dependent. So area is a function of radius. For the pizza area, we see that this is a function, yes, but it's non-linear. For the sauce, we see that it's also a function, because we knew that, and this is a linear function. We again have a table. This table is showing the number of cuts and the fraction of original area remaining. I want you to go ahead and complete the ordered pair, and I want you to graph it, and then check back with me. Let's see how you did. Check your ordered pairs. If you have any questions, make sure you ask me tomorrow. And here you see a graph, and your graph goes like this. So what does that tell us? Interesting questions here for you to think about. If you start with a piece of paper in your hand and repeatedly cut the paper in half, will your hand ever be truly empty? Go ahead and take a guess, and we'll talk about it in class tomorrow. And then explain whether or not the remaining area will ever reach 0. We've already talked a bit about functions, and we will be writing some function rules. A function can be thought of as a rule that you apply to an input or an x value in order to get the output or a y value. And nonlinear functions can be described with words or with an equation or a graph or a table, just like linear functions. Let's take a look at problem number 2. Here we have a table, and this table is representing the figures to the left. Figure 1 has 3 new branches. Figure 2 has 9 new branches. Figure 3 has 24 new branches. As we work on, we will find what the other ones have. Can you stop this video and work through and see if you can find the pattern? Please do that and then start the video up again. Okay, well, the pattern in the table is that the number of new branches is 3 times the number of branches in the previous figure. So as we work through this, it comes down the number of new branches equals 3 raised to the power of the figure. So the equation that represents this function is y equals 3 raised to the x power. So when x is 4, y is going to equal 81. When x is 5, y is going to equal 243. And you can put that in the table above. So we should go ahead and fill in the ordered pairs we know. And graph them at the chart to the right. And draw our line. As you can see, it's a function, but it's a nonlinear function. You can think of a function as a rule that you apply to the input, or the x value, in order to get the output, the y value. You can describe a nonlinear function with words and equation, just as you did with linear functions. This is problem 3 in your notes. And we're going to take the function represented at the very top in purple and fill out our table: 1, 1, 2, 4, 3, 9, 4, 16, and 5, 25. Now we need to find some words to explain this relationship. So look at it closely and see if you can figure out the relationship. The y value is found. How is it found? Do you have it yet? By squaring the x value. So if we want to write an equation, we know that y value is equals x squared. Take a moment, please. Stop the video. Work through both the lesson check and the math success. And then turn this back on and check your work. Well, how'd you do? Remember to write down any questions you have and bring them to class tomorrow.